Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn about convolutional neural networks with TensorFlow and Keras. Today we will be training a simple convolutional neural network for image classification on MNIST digits. So this network will achieve over 99% accuracy on the MNIST dataset. Now, in this tutorial, we will use the Keras sequential API for creating and training our model. And this is the simplest way to use TF Keras. So as of the day of the recording of this video, which is March 2019, right now we are on TensorFlow Alpha for 2.0. TensorFlow 2.0 was announced. Very exciting. It's revolutionizing the deep learning. We're entering a new era of TensorFlow 2.0 and beyond. And as of today, it's an alpha, but the stable release is coming any time. So here we're going to go ahead and import TensorFlow, but before that we're going to just make sure that we have installed TensorFlow GPU, because best practice, of course, we're training on GPUs, we're doing deep learning. So here with this exclamation mark, you can run a bash command here in a Jupyter notebook. So you just run a pip install of TensorFlow GPU 2.0 alpha. And so here to set this up, I simply created a virtual environment with Anaconda and installed Python 3.7 and Jupyter. So here we import TensorFlow STF, and then from TensorFlow.Keras, which is what we care about the most, we're going to import three modules: datasets, layers, and models. And in a moment you'll see how we use those. So the first step here, the next step is to download and prepare the MNIST dataset. So here we're going to call the load data function from the datasets.mnist module. And this is going to download from storage Google APIs, is going to download our data, our MNIST dataset here for TF Keras. So we have our train images and train labels as a tuple here, and our test images and test labels as another tuple. So what we want to do first is we want to reshape the train images and the test images. When we download them, we get them without this last dimension here. So the dimensions here that we have for our data set is batch size, height, width, and then color channels. So when we do the load data from datasets.mnist, we get the data without the color channel dimension here. So we just want to reshape it and add this color channel dimension. So now, why is it 1? Because we're dealing with grayscale images. Now, if these were color images, we would have RGB, red, green, and blue, so 3 color channels. But these are grayscale, which is just 1 color channel. Height and width of the pixels, so 28 pixels by 28 pixels, height and width. And this is the batch size. So for the train images, we have 60,000 images total. And then for the test images, we have 10,000 images. So in this case, it represents the batch size, but in this case, because we have the full amount, we haven't split anything, it's just the full amount, the whole data. The amount of images, the shape, height and width, and then the color channel. So that's what we have. And now, best practice is to normalize your pixel values to be between 0 and 1. And you do that by just dividing the train images by 255. So in color channels, or even grayscale, they range from 0 to 255. So we just want to divide by 255 each one of those, so they're all in the same scale from 0 to 1. That will just normalize. And it's best practice to normalize your data for the stability of your neural network and to make training better and more efficient and faster. So it's just that we normalize the data. You always want to do that. Now you can also do further normalization, like batch normalization within your network on a batch per batch basis, but that's a little bit beyond the scope of this video. So let's go to the next step, which is create the convolutional base. So we want to start creating our model, our neural network, and again we're using the tf.keras sequential. So the sequential API for TF Keras. So here we're going to create a very simple convolutional network, and we've learned this before. So the first step really is just to create a model variable here. So our model, and we're going to assign models.sequential. Remember, we imported models, and we just want to grab a sequential object here. So we have a sequential model, and this is just a sequential layer. So just one layer after the next. You can think of it as a linear model. And then we want to add layers. So this model, our sequential model, has an add method here. Our model instance has an add method. So we're going to add layers. So again, we imported, let's go back real quick, see, so we imported layers and models. So we have models and then layers, and from layers we can access the layers that we want. So for our model, since we're doing, it's a CNN, it's a convolutional neural network, we're using the basic structure of a CNN, which is conv2D, so convolutional layer, and then activation, ReLU typically, and then max pooling layer. So here in code and with Keras we have model.add, and then we pass in as the parameters here. So first we have the actual layer. So we have layers.conv2D, convolutional layer, and then your convolutional layer here has several parameters. So here, this is the feature map. So the output feature maps here for this layer. So this layer is going to output 32 feature maps. That's the first parameter, and the output, and then the second parameter here is a tuple containing the convolution filter shape, the shape of the convolution filter, which is what scans through the image. So we're going to do a 3x3 here, and then the next parameter here is the activation, which is very nice here with Keras. Right here, you can in your layers.com and inside your layer, you can just simply add the activation. So the output of this convolutional layer will just apply an activation function. In this case, we'll use ReLU, as this is very standard transform our output using ReLU. And then the last parameter that we're using is the input shape. And the input shape parameters here, we only have it for the first layer because this is the input layer of our network. So the input shape is say 28 by 28 by 1. Now the CNN here in Keras takes tensors of shape, image height, image width, and color channels, which is what we have here, but it ignores the batch size. So that's why this is the input shape. So we have our convolutional layer here that we added to our model, and with its corresponding ReLU activation. And then for the next layer, we're going to add, same thing, model.add, and then layers.max pooling 2D. So it's a max pool layer, and this is again just downsamples the image. So we're choosing a 2x2, so we'll just downsample it by half. So this is the filter, the max pooling filter that does that downsampling. So these are the dimensions, pretty standard. And now it's a sequential layer, it's a CNN, so we want to add another convolutional layer, another stack of convolution with ReLU activation and max pooling. So we're just going to add another one. And here we don't need the input shape anymore, so same as before. And then and this is an arbitrary architecture here, just to keep it simple, to show you how to create a convolutional neural network with TensorFlow and Keras. So for the last one, we just add model.add method and then pass in layers.conv2D with an activation of ReLU. That's it, and we just choose not to downsample for this last one. So let's display the architecture that we have so far. Again, so it's a sequential model, and then here when you can actually call this summary method on your model instance, sequential model instance, and it will print out this nice representation of your model architecture. So we have our layer type, so conv2D, the first convolutional layer, and it shows you the output shape for that. So again, it ignores the batch size. So we have 26, and then 32, and it shows you the number of parameters here. Now this 26 is based on just how the convolutional layer is going through the input initially. So this is, but the point is that it's showing you the output shape for each one of your layers. So here you can know precisely what is the output shape. It's very convenient. Then the number of learnable parameters, and here we're not really setting any hyperparameters at this point. So far, it's really just learnable parameters, so the weights and the biases associated with our layers. So we do some. Now the next is the max pooling layer. And as you can see, it downsamples the image by half. So 26 goes 13, and then it's the same number of output feature maps, which is 32. It's just downsampling them, reducing the number of parameters essentially. So as you go into deeper into the network. So now we have our next convolutional layer that we added here, and now we have more learnable parameters. Why? Because now the output of the second one is 64. So we won't be first having 32 output feature maps for the first convolutional layer, and then for the second one we have 64. So now we have a lot more learnable parameters. We have a lot more output feature maps here for the second convolutional layer. And again, we apply max pooling again, and it goes by half. Now half would be 5.5 of 11, but actually rounds down when you in practice when you do it. So that's why it goes to 5. And now for our last layer, we have another convolutional layer, our last one, and it also has 64. Now there's more parameters, essentially twice, because here are the mapping that we're doing here we're going from 32 to 64, and now here we're going from 64 to 64. So that's why we have more learnable parameters here. And depending on the architecture, these numbers will vary, of course. And then here, this model summary will also tell us our total number of parameters, both the trainable and non-trainable parameters. And the non-trainable is what we would normally refer to as the hyperparameters, the ones that we set. So 55,744 learnable parameters or trainable parameters, which is pretty amazing. So our model will learn the optimal values, will optimize for the values for each one of those parameters to find the best function that maps our inputs to outputs. So the next step is to add dense layers on the top. So it's not enough to just have the convolution layer and then ReLU activation and max pooling. Now we need to. Now the next step is to flatten our output tensors. We want to actually put it through what we would normally refer to as a fully connected layer. So just or here we call it a dense layer with tf.keras. So very simple. So our model, we're going to add another layer, and from layers we just grab flatten here, and this is a layer object here. So from layers.flatten, and then we just call the add method on our model. So this flatten will take our tensor, which is a tensor of rank 3 or a 3D tensor, and just flatten it into a tensor of rank 1 or a 1D tensor, which is what we would call a vector. So we're grabbing the three dimensions here of our tensor, and then just putting them all together, stacking them all together into just one dimension. So that dimension is going to be 64 by 3 by 3, just reshaping it. So we do that. And then we're going to add another layer here, which is a dense layer, and we're going to choose 64 neurons for that layer, and for its activation parameter, we're going to choose ReLU again. And that's it. We're only going to add one more layer here, which is just the output, and this is going to be different. So again, model.add, and then pass in a dense layer, but the output will be 10 with activation of softmax. Why? Because we're doing categorical cross classification. So this is an image classification task where we're classifying the 10 output classes for the MNIST. So MNIST has 10 output classes, 10 possibilities, and for categorical cross entropy, you would do a softmax here, activation for classifying multiple classes. So that's why we have a dense layer with 10 outputs and softmax. So each one of these 10 will correspond to one of the possibilities. So the digits ranging from 0 to 9. So let's actually call our summary method on our model here again. And so we have our sequential model again, and we have the layers that we had before. And now what's changed here is now that we have added a flattened layer, which again will take our tensor of rank 3 and reshape it or flatten it into a tensor of rank 1 or a vector. This is just a vector with 576 entries or dimensions. You can look at it that way. But it's flattened. If you multiply 64 by 3 by 3, you get 576. So it's the same. It's this tensor is just being reshaped. So we can actually have it in because we need it in this flat format, so we can push it into our last dense layers to get an actual output for classification. So we have the 64 neurons here for our dense layer, and then 10 for that last one. Here the number of parameters, learnable parameters, doesn't change for this dense layer. Why? Because nothing's really changed. We really just reshaped the tensor. And for that last one, we have 650 learnable parameters. So where does that come from? So we have 64 and 10 so the weights connecting these two dense layers. So you should have 64 by 10 times 10, so 640 for the weights, 640 parameters. So why 650? Where's the other 10 come from? Well, each one of these 10 neurons here in the last layer, the output layer, has also a bias associated with it. So remember, we have weights and we also have biases. So we have the 64 by 10, so 640 weight parameters, and then plus 10, one for each one of those nodes. So 650 is what we have in total. So now our total number of parameters now here comes out to be 93,322. And still haven't set any trainable parameters at this point. So that's our model architecture. Very simple and very straightforward convolutional neural network, and works very well in practice. And of course, there's more that you can do. You can add batch normalization, and you can make it more robust and do other things based on performance. But for this simple case of MNIST digit classification for 10 classes, this will give us excellent accuracy, and you'll see in a moment. So now we're going to compile and train the model. So with TensorFlow and Keras, it's very simple how you do it. So we call the compile method on our model instance, sequential model instance, and this just basically sets the configuration for our model. So here we set the optimizer, so the gradient descent optimizer, and we're choosing Atom. And there's others, you can do SGD, and there's other ones, Adagrad, but we're choosing Atom. In practice, this one works the best usually. And here you don't, and as you notice, we're passing strings, which is very, very nice, but you don't have to pass strings. You can also use the modules directly. You can say tf.keras and just grab the modules and the functions directly from there, but you also have the option to do it very simply with strings here. So for optimizer, we pass Atom, and of course, these names have to match the name of those functions. You're just leaving the parentheses out for the constructors. So just Atom for optimizer, and then for loss, we have a loss. And this is how, so what is the problem here? We're doing image classification for multiple classes. So we're doing categorical cross entropy. So for loss, we're going to pass in sparse categorical cross entropy. Of course, makes sense. It has to match. And then for our metrics, see what are we tracking? What is the metric that we're trying to optimize? The metric or metrics that we care the most about. So it's a list, and you can pass in more than one, but here we just chose the accuracy for our metrics. And all of these have corresponding modules in TensorFlow.keras that you can access those that way as well. So we compile our model, and then, so that sets the configuration, and then we call now the fit method on our model. And this is essentially what runs the training. This is what runs the training with our configuration here. And this is what's going to now start to optimize our learnable parameters and start to increase our metric that we chose, which is the accuracy. So here we picked 20 epochs. This is a hyperparameter that you can tune, that you can choose arbitrarily. We just chose 20. Even 5 would have been enough for this simple example. So, and we pass our train images and our train labels that we had before, that we normalized, that we downloaded and normalized, and our epochs. We call the fit, boom, and as you can see, for each epoch, we have it's running through all of the images. Here we didn't really batch it up in this case. It's just a simple example, and we're running on GPU. Remember, we actually installed TensorFlow GPU, so in this case we're running on GPU, and this is what you want to do in practice always. So as you can see, the accuracy just steadily increases, and it's basically reaches a maximum here, and it's over 99%. And by the way, you can actually open up TensorBoard as well. That's out of the scope for this video, but you have the option and with TensorFlow Keras now also to register this in TensorBoard and look at your metrics and a bunch of other things with TensorBoard, which is very nice. So now here at the end, we just have our test loss and our test accuracy, and we just call model.evaluate. So we have the fit for training, and we have a evaluate for evaluation. So we call evaluate on our model instance, and we just pass the test images and the test labels. So here's the train images and train labels, and here we pass the test images and test labels. So we evaluate, and then let's print, and then we print our test accuracy here, and you can see it's over 99%. So very, very, very nice, high accuracy, and very simple way to train with TensorFlow Keras, it's CNN. So thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.